Hi students, as we have discussed in a previous video about something small about our cache memory. So now we are going to discuss about uh, some more details or going deep towards our cache memory. First of all, we have discussed about our heat ratio, then miss ratio, heat time, miss penalty, all these. Uh, I don't remember that I have discussed about miss penalty. What is miss penalty? Nothing that like a penalty. It is the time loss or time delay. Okay. When we are searching a cache for our data, but the data is not present in our cache, that's the time is wasted or the time delay is called actually miss penalty. Okay. Let's move a deeper towards our cache memory. Okay. First of all, we are going to discuss about cache components. Uh, uh, Discuss our cache components. First of all, there is two operations. Okay. One is read operation and another one is write operation. Okay. Read operation and another one is write operation. Okay. Um, when we read, while we are requesting data from our main memory, we are going to read in the cache memory. If the data is not present, then it read miss, or data is present is a read hit or cache hit. Okay. Then let's go towards our write operation. Write occurs towards from our CPU. The write signal goes to the main memory. The data is write in our cache and main memory. Okay. While we are writing the data in cache memory, if the data is already present in the cache, then it's a write hit. Okay. If the data is not present in the cache while we are going to write, then it's a write miss. Simple, not more complex. Okay. Then we move towards our components in cache memory. Okay. Be careful and be attentive, because this is our okay, this is the main chapter that cache components. Okay. There are mainly three cache components. One is cache block. Okay. Then another one is comparator. Another one is a cache controller. Okay. Cache controller, as you are noticing from the name, it is one type of manager inside the cache. Then this is our cache block. We will later discuss about cache block. Then our main thing is our cache comparator. Okay. Cache comparator. While we are searching data inside the cache, we are not searching the data, we are searching its address. Okay. Its address, we are searching the address, and the cache comparator checks the address matches. Okay. Take the address and check it, is it matches or not matches. Okay. If the address is matched, then it's definitely hit, and if it missed, then no address matched. Simple. Okay. Then cache controller mainly help to manage our cache, which data is to come, which data is to stored, which data is to be replaced. Okay, all these are controlled by our cache controller. Okay, three components. And then we will move towards our cache block. We will move towards our cache block. Okay. As we have discussed about three parts mainly. one is tag, another is data, and this is our metadata bit. Okay, we have discussed about in our previous video. Okay, let's discuss more and more clearly. Okay, if you are going deeper, then actually the cache have two parts. Actually the cache have two parts. One is our data, and another is metadata 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 bit. Okay, then what is the metadata bit? Actually the metadata bit is nothing about the data, it is only about the data. How? In metadata bit, we also consider our tag bit. Okay, then another our valid bit, then another one is our data bit. Okay, all these two extra bits are called our metadata bit. Metadata bit means symbol that is store some information about our cache data, the data inside the cache block, and the information about that data is stored in metadata bit. Okay, this is our cache block, simple and clearer. I think you are clear about the cache block. Then we will move towards the partitioning. I have told that there is a tag bit. Actually, what is the tag bit? A tag bit actually the associated address with the data. Okay, let this is our cache. Okay, this is maybe the cache tag. Okay, actually maybe this is our memory. Okay, this is our memory maybe. This is the data have a address. Which address? The data in the cache is also in the memory. Okay, the address of the memory is stored as a tag bit. Okay, as a tag bit. If the tag bit matches, then the data in this address is also available in the cache memory. Okay, this is the tag bit, means the address associated with the data. Okay, then we also discussed about valid bit inside our metadata bit. What is valid bit have two values, one is 0 and one is 1. 0 means there is a data or meaningless data. Okay, if the data block has a data which is meaningless, then it is 0, it's invalid. Okay, if the valid bit is 1, then it's a valid data and a meaningful data. Okay, while there is also, you have to know, or you will listen sometime, that data bit. Then what is data bit? Actually, what is the data bit? Okay, and data bit simply tells that the data inside the cache block is modified or not. Okay, how? If the data bit is 1, also the data bit has two values, 1 and 0. If the data bit is 1, then what? The data in the memory and data in the cache, okay, in same address, or in same associated address. Okay, data is different. Data is different in both addresses, in memory and cache, associated with same address. Okay, this is 1, data bit is 1, while the data bit is 0. Okay, while the data bit is 0, then what does it mean? 0 means the data is same in the memory and cache associated with same address. Okay, this is the work of data bit. Okay, these bits are also includes in our validity bit, sorry, in our metadata bit, okay. Then we will let's move towards our uh, cache mapping. Okay, this is a cache memory, okay. This is cache lines, sometimes this is called way, sorry, this is our byte inside the line, this is the line, okay. This is the line, let me make it clear, okay. I'm zooming the image, and this is a line, okay. This is another line, this is another line, okay. This is another line, okay. These are the cache lines, okay. And inside the cache lines there is data byte, okay. Then let's move towards our, then what is cache line? Okay, the cache line, this is the cache line, is same as, this is our memory, one block, okay, one block. If there is no partitioning inside the block, okay. If there is partitioning like a word, if the memory block has 4 words, if the memory block has, for this is our memory block, let's say I'm dividing this also, okay. This is a memory block and this is a memory word, okay. The full block is stored inside the cache line. The total block is stored inside the cache line, okay. It is clearer, that the whole cache, sorry, whole memory block is stored in the cache line. Is this clearer? This is a cache memory, smaller compared to the main memory. There are millions or billions of addresses, there is limited addresses, but a memory block is fully loaded or can be fully loaded inside a cache memory line or cache line. Clearer? Then okay, here is how the address partition occurs. Here is our block number, which block number is our CPU searching, okay. Here the block numbers, these are the block numbers, 8 block number, 4 block number, 0 block number, 65,528 block number, okay. All these numbers are provided here. The CPU will search the logical address, then the logical address is converted to the physical address through memory management unit, okay. Physical address, okay. The block number is actually the address of the block. Then what is the byte offset? Byte offset means the word inside the memory, okay. I have discussed that we have broken the block into four parts, okay. These are actually words, the byte offset tells the particular word in this section or in this section or in this section or in this section, okay. This is clear. There is a 4 partition, okay. Let's make it clear. Partition 1, partition 2, partition 3, partition 4. Then if there is 4 partition, then 0 0 0 1 1 0 1 1, these are the address of these 4 words. Then the byte offset, okay, the byte offset may be of 2 bits, Okay, if the byte offset is 0 0, then we are addressing to this block. If the byte address is 0 1 is 1 0, let's the byte address is 1 0, means addressing to this data word or this word. Okay, that's like the byte address is actually the particular address of the data, inside the block. Okay, and this is the a block number. Okay, and this is the address, and this address is sourced inside the cache. And who sourced inside the cache? Comparator. Who search? Comparator. It is a hardware component. Okay, it is a hardware component. Okay, let's make it clean. Then let's move towards our cache mapping. Okay, here is some flowchart or how the cache works, a read cycle operation. Okay, let's move. First started a processor output a memory address. Okay, processor give a memory address or request memory address. Then find the memory block B that contain address A. Where it is searching, find the memory block that contain the address A, means searching the address inside the cache. Each block B in the cache is searching the address. If the address matches, then the cache block is available. If yes, then it is a hit. If yes, this is a hit, cache hit. Then if no, then miss. Okay, if hit, then supply the word at the address A. Okay, supplying the word to the CPU. Okay, if there is a cache miss, let's move. If there is cache miss, initiate access to a memory block B. Then we are going to the actual address of memory. Then assign cache line C for memory block B. Okay, we are storing the data in cache. Then okay, storing the data, we are trying to storing the data. Here we are trying to storing, we have not stored till now, we are trying to store the data. Okay, then fast checking, is our cache empty or there is cache is full. If the cache is full, then there is a replacement algorithm works. Replace a cache line. Okay, how we can replace the cache line? Uses replacement policy. We use some policies to replacement the cache block or storing or replacing a data in that from the cache block. Okay, if the cache memory is not empty, then we are storing the word. Okay, here in the flowchart. Okay, is cache line C is free? Is the cache is free? Is the cache line C is free? If free, if yes, then the data is stored in that place. If no, then replacement policy works. Okay, then load memory block into our cache line. Okay, then you have to understand one thing. When the data is loaded, it first loaded to the cache, then it loaded to the CPU. Okay, now we will discuss about two things. One is locality of reference, another one is locality of reference, and two parts of the locality of reference. There is actually two parts. One is temporal locality and spatial locality. A locality of reference means which data we are using, on which basis or which reference we are storing the data inside the cache. Okay, on what basis we are storing the data inside the cache. Okay, this is called locality of reference. Okay, the locality of reference have two parts. One is temporal locality, one is spatial locality. Okay, what is temporal locality saying? The temporal locality saying that if there is a chance of repetitive use of same data. There is a chance of repetitive use of same data which is used by the CPU. If CPU is using a data, then there is a chance of repetitive use. Okay, let our CPU use A, then there is a chance of repetitive use of the same A. So our system stores the data inside the cache. Let here is a cache. Okay, the A is stored inside the cache. Then this is then let's discuss about a spatial locality. Okay, what is special about spatial locality? In spatial locality, actually we don't store the data which is now used. Okay, we also store the A inside the cache, but we don't again store our A. Okay, what we store? We store the nearest data, the nearest data of A. Okay, there may be chance of use of the nearest data of the actual data. Okay, there may be chance of the need of nearest data of the actual data. Okay, so we are taking the nearest data to the cache also. Okay, we are taking the actual data, then we are taking the nearest data. Okay, these are the locality of reference. One is two part, temporal locality and spatial locality. Temporal locality means just saying that if you are using a data, then there is a chance that there may be repetitive use of the same data. Okay, then spatial locality means if you are using the a data, then there may be a chance of there may be a need of the nearest data of the actual data. Okay, these are the two concepts of locality of reference. Let's move towards our mapping techniques. Okay, these are the mapping functions. Now we are discussing about mapping function, also called cache mapping. First of all, there are three types of cache mapping. One is direct mapping, then another one is set associative mapping, and third one is associative mapping. Okay, let's zooming in. Okay, first of all, the associative mapping is also called fully associative. Okay, fully associative. Okay, you don't need to confuse among associative and fully associative. Both are the same. Okay, then what is direct mapping? Direct mapping? Uh, Here some data is already given. It specifies a single cache line for each memory block. Okay, specifies a single cache line for each memory block. Okay, what do you mean by that? That there is a specific cache line for some memory location, some memory blocks. Okay, that there may be a chance of a single cache line, maybe this is a line 1 is linked to more than one memory location 1, memory location 2, memory location 3. Okay, there may be a chance that a cache line is associated or connected, or maybe handle more than one memory locations. There may be chance. Okay, then there is no concept of sets. Okay, we will further discuss about sets in our set associative, but you have to understand that no concept of set in our direct mapping. Okay, let's move. Actually, how it works? First we use a modular function. Okay, how we just take module. Okay, let's we have here we use a 4 module direct mapping. Okay, 4 module, 4 lines. Okay, 4 lines. The module value depend upon the number of lines. If there is 4 lines, then we will make modulus with 4. Okay. These are main memory addresses. These are main memory addresses and 16 blocks. 16 blocks while 4 lines. Then how we do this? Now 16 mod 4. Okay. Let's discuss how it actually occurs. How it actually occurs. Then this is the block address 15. This is the block address 15. Okay. Then in which cache line it will be stored? Now 15 mod 4. Okay. 15 mod 4, that is 3. It will be stored in third cache line. Okay. Let's discuss about 12. Then come 12 mod 4, then gives 0. Then this block is mapped to 0 cache line. Okay. Then let's discuss about 9. Then 9 mod 4. Okay. 9 mod 4. What? 1. Then first line, the 9th block is mapped to the first cache line. Okay. Let's clear it. That block address, block number, mod line number. Okay. This is how it works inside our direct mapping. Okay. Block number 10 mod line number, cache line number 4. Number of lines in cache 4. Then 2. Okay. Then let's move towards some example. Okay. Then move towards some example. First, you have to assume that a block address 0. There is nothing inside our cache. Memory. Okay. Then first our CPU request a block address of 0. Then there definite nothing inside the cache. Then there will be a miss. But that time the block 0 is loaded to the cache block 0. How? 0 mod 4, because our cache is of 4 line. Okay, it gives 0. So in block 0 is loaded to our cache line 0. Block 0 is loaded to our cache line 0. Okay. Then our CPU request a 4 block. Then what happened? Already a block 0 inside our cache. Block 0 is inside our cache, but we are requesting a block 4. Block 4 not inside the cache. Then there will be a miss. And while there is a miss, then the block 4 is mapped to the, or will be stored to the cache memory. Then it have to map. Then the block number is 4. The block number is 4. Then what the number of cache lines 4 is equal to 0. Okay. This is also stored in our cache line 0. Okay. In cache line there are already a block 0 is available inside the cache line 0. Then how we just replace the cache line we just replace the block 0 on cache line 0 and enter the block 4 there. Okay, and this repeatedly occurs. Okay, this repeatedly occurs. Okay, you will fill here. You have to understand the table. Okay, let's move towards next table. This is also direct mapping. Here direct mapped cache states. For example, here there is different blocks. Okay, in zeroth block, okay, first our cache is empty. Then if the CPU is requesting a zeroth block, then there will be miss. Definitely there will be miss. Then the block 0 is loaded to which cache line? We have to zeroth block mod 4. Okay, is equal to 0. Then in zeroth line the zeroth block is loaded. In zeroth cache line the block 0 is loaded. Okay, then 7, we are requesting a 7, but in our cache only a zeroth block is available, only block 0 is available, but we are requesting a 7, then it's definitely miss. Okay, and then 7 mod 4, which is 3, at the block 7 is mapped to the cache line 3. Okay, you can understand from the memory. Then let's move some more example. Then here is our 9. Here is our 9. Then there is only block 0, then block 7 is inside the cache. Okay, then we are searching the block 9, which is not available. Then there is a miss, and block 9 will be mapped to 9 mod 4, which is 1. The first cache line will store the 9th block. Okay, the block 9 is stored in cache line 1. Okay, simple. This is simple, and you can check here. Okay, from here the cache is full. Okay, initially the cache is empty, so there is this is a compulsory miss. When we start our system, usually our cache is empty. Okay, when the cache is empty, there is also cache miss occurs. These cache misses are called compulsory miss. Okay, compulsory miss. Okay, next move towards our fully associative. Okay, let's see our how address partition occurs. Here is our address, what a CPU sends. Okay, what CPU sends, and how we find this. Okay, how this address is generated? This address is generated through our memory management unit. This address is generated by our memory management unit. Okay, can you define what is logical address and what is physical address? Physical address and logical address. Okay, if I will give some example that there is a room which number 205. Okay, 205 room in a hotel. Okay, it is the logical address. But if we are saying that the 205, I don't say 205, I will say in second floor the first room. Okay, second floor first room, from the right. Okay, from the right, then this is the physical address. This is the actual physical address, and the room number 205 is the logical address. 205 is the logical address. Okay, for logical address we have to search everything. Maybe there is a search for everything, but in the physical address we have the physical address. Okay, then this address is generated by our memory management unit. Okay, Then this is our tag bit. This is our tag bit. The tag is associated with our cache block or cache data. This is our tag bit. Then this is a cache line. This is a cache line. Okay, what is cache line? There are 4 line address. There are 4 line address. Okay, then 4 lines. Then we will use 0 0 0 1 1 0, then 1 1 1 1 for this addressing of the lines. So these are the 0 0 0 1 1 0 1 1. Okay, these are 2 bits for cache line. Cache line bits are according to the available of cache line. Okay, then our b bits. Byte offset means the exact data. Okay, these are, okay, if there are four words inside a cache data, then the actual data, how can you find the actual data? The actual data is find through the byte offset value. Okay, these are also, we can say 0 0 0 1 1 0 1 1. Okay, so we can find the byte offset by 0 1, then this data. If till 1 1, then this data. Okay, these are the byte offset. Let's make it clear, make it more clear. This is very important, that the cache tag. What is the cache tag? We have discussed your tag address. You remember? The cache tag will be checked or matched with the cache tag bit. Okay, the tag bit and the cache tag. If the cache tag and the tag bit matched, then there is a cache hit. And this is the cache line. Okay, this is a cache line, and this is the cache line address. Okay, in the line there is 4 words. Okay, the each word's address is a byte offset. Okay, bytes offset means the address of the byte. This byte have some different, this byte have some different, this byte have some different address, and this byte have some different address. Okay, it's clear. This is our direct mapping, all about the direct mapping. Okay, there are some examples we have already discussed. And this is our associative mapping. Also called fully associative. Fully associative mapping. Okay, what is here? And a cache tag and byte offset. Here is actually no line address, no line bit or line address. Why no line bit or line address? Because in associative mapping, if there is empty spaces, then the memory blocks can randomly map to any cache block. Sorry for the interruption. What is saying in associative mapping? If there is empty blocks inside the cache, and then a memory block randomly mapped to any of the block inside the cache. If there is empty, if it is full, then cache replacement policy will be works. Okay, so here is no particularly specific cache block or cache line for a specific address data. This is randomly data is stored in the cache, so there is no line address. Okay, while in our direct mapping there is cache line bits. Okay, then there may be a question in your mind that if there is a 4 to 5 empty cell, 5 empty blocks inside the cache or empty cells inside the cache, then how or who decide the data is stored inside which empty cell? There is 5 empty cell, maybe. Now this is a cache. Let's there is 5 empty blocks. Okay, where I am seeing it combinedly. Okay, let's there are 5 empty block, 1 2 3 4 and 5. Okay, who decide that in which block the data will be stored? Actually this this decision is taken by our controller, cache controller, cache controller. Okay, this decision is taken through our cache controller. Okay, let's move towards some example. Fully associative cache states, for example, in associative mapping, from when initial our system will there will compulsory miss as I have discussed that while we are starting our system, the cache memory is empty, so there is compulsory miss. This compulsory miss. Okay, when we are using 0, when we are using 0, then there is a miss because no data inside the cache. Then the 0 is randomly assigned to the cache line 0. Then our CPU request block 4, then there is always miss because the the block 0 is only available inside the cache line 0. When you requesting block 4, then the block 4 is stored inside the cache line 1 and there is a miss. Then again, if you are using a block 0 or requesting a block 0, then it checks inside the cache and block 0 is already in your line 0, then there is a hit. Okay, while there is request for 0, in that time there is block 0. Okay, you have to look at the previous. There is block 0 and block 4 inside the cache memory. Okay, then we are searching for block 0 and block 0 is always available, so there is a hit. Okay, in next we are searching for 8. Okay, but in our cache there is block 0 and block 4 present. Block 8 is not present, then they'll definitely miss. And the block 8 is randomly stored inside the cache line 2. Okay, then the block 0 is requested and the block 0 is requested. Then in previous block 0 available, block 4 available, block 8 available, then block 0 is available, then there is a hit. Okay, you can elaborate the example. Here is hit ratio. I have discussed our hit ratio, miss ratio. Okay, then here is some example of mapping function, how actually it occurs. Here tag address from address bus. The CPU send a address, okay, through the address bus, and the address bus is compared to the tag. Okay, this is a tag. If match 0, match 1, okay, match 2c minus 1, all this the comparator checks if the address matched or not. Okay, if it's matched, send to the CPU. Okay, we have discussed about our direct mapping and fully associative mapping. Okay, in next video we will discuss about our set associative mapping. Okay, thank you.